pH itself is actually, it's a very abstract phenomenon. I mean, pH is a much more complicated thing than most people actually give credit to it. And to take it down to a level where you can get students at Key Stage 3 and Key Stage 4 understanding that is a very difficult thing to do. What we're going to do now, anybody tell me what is that? Jessica?
Is it a pH scale?
It is, thank you, well done. We've got 1 through to 14. Can anybody tell me then, where is the strong acid, the strong alkali, and the neutral part of this pH scale?
It's neutral 7.
It is, well done. Okay, so which is the strong acid, which is the strong alkali?
The
Sophia?
strong acid is number 1, isn't it?
Brilliant, thank you very much. And therefore strong alkali must be this side?
Yeah.
Great, well done. We're trying to get you to understand what really is an acid and what really is an alkali. Okay? Now, you know what H2SO4 is, sulfuric acid. You know hydrochloric acid is HCl. You know that nitric acid is HNO3. Can anybody then tell me, if you look at that diagram on the board there, or that kind of picture we've got, which one of those are acids and which one of those are not acids and therefore, in this case, alkalis? Jordan?
Would HNO3 be acid?
Good, well done. So HNO3 is acid. What we're looking for here, we're looking for distinguishing features about the acids are always in common. Over there, Zoe, please.
Won't H2SO4 be an acid?
H2SO4, fantastic, thank you. Okay, and any others? Because there are a few more on there. Ollie?
Will HF be an acid?
HF, it would. Now, we've now started to get a pattern emerging and I'm hoping that more people are starting to see what the pattern is. Caroline?
Is it everything with a H? No, it's acid.
No, keep going.
Everything with is it hydrogen?
It is, it's
It's
hydrogen.
it's an acid.
Yeah, okay. H, H2, this has got 2, and HF. So everything with a H at the beginning is how we write acids. And the common thing about an alkali is what? The OH. You have an OH, which is an hydroxide ion. Okay? So this, all these here, are alkalis. You've tested pH before, haven't you?
Yeah.
What did you use? pH scale, fantastic. And we have all the different colours. How accurate is that?
Not very.
It's not entirely accurate because we have 4, 5, 5.5, 6. There are a few divisions here and there, but it's not entirely accurate for that reason. So, let's think of a more accurate way to do it. And I think you've pretty much guessed because it's set up in front of you. But we're going to use a pH probe. Okay? There it is. But what I'm going to do is I'm going to get the computer to plot the pH as I allow this to fall through the burette. What I've got in here, I have in here 25 centimeters cubed of hydrochloric acid. So, and in here I have my sodium hydroxide, okay, which is my alkaline. Now, when I start this off, what pH is it going to read? 7? It's an acid. It's inside an acid. There it is.
Oh, low.
It'll be about 1 or 2 in it because it's an acid.
Good. We're going to start at a pH quite low. What do you think is going to happen to the pH as we allow the alkali to drop into that solution there? Dom?
Will it slowly neutralise?
It will neutralise. Well done. Okay, so you'll find the pH will change, but is it going to go up? It's going to go down? What's going to happen?
It's going to go up.
So the pH is actually going to go up. How do you think it's going to go up? Is anybody brave enough here to come up and have a squiggle on my board and actually predict what it might look like? Come on then, Caroline.
Oh!
Steady.
that.
Okay, thank you very much. All right. That's not a bad idea. I can understand where she's coming from. She's kind of predicting that as we drop the alkali in, you're going to get more and more towards pH 7. Not straight away. It's going to take a bit of time. And then, as we go past the point of neutralization, because we add, and this is what I like about what Caroline's done, she's actually said as we go past the point of neutralization, the pH will keep going up, which is good. Because most people stop at 7 and forget then. So that was really good. Right. Yes, Dom?
Would it neutralise faster as it got more neutral? Because it doesn't have as much acid to
Right.
react against.
Good idea. So you think it might actually be a bit steeper?
Yeah,
So
yeah.
more like a curve.
Yeah, but so that it's continuous.
So it's continuous. Right. Okay. Well, I'll tell you what. It's not a bad idea. I quite like the idea. But the main thing is, what we're seeing here is that the pH goes up, we go past neutral, and I like the idea, and you're thinking maybe we're going to go faster than what Caroline says. Okay? Right, let's have a go then. I'm going to pop it in. So what this is a little magnetic stirrer. Place it inside. So, the pH sensor is inside the acid. The stirrer is stirring things up nicely. We're going to allow the alkali to drop in by just turning this tap here, and it will drop at a regular rate. And then we're going to get the computer to actually plot the pH as time goes along. Okay? Now I'm going to put it on the continuous mode so that we don't run out of time. Okay, so we've got a pH of around about 1.6, much more accurate than a pH scale. Okay, because this will not only tell you what kind of colour it is, roughly what kind of pH it is. And what we're going to do is we're going to allow this to start dropping in, and we're going to start produce the curve. Here we go. Now I don't want it to go too fast. I want it to go relatively at a steady pace. There we go. So we're dropping roughly about 1 centimetre cubed of alkaline every second. Now the pH is now starting to rise. It's starting to go up. Now we're going up. Now this is what Dom predicted. Dom predicted it would go up and relatively steeply, and I think that's pretty much what's happening now. And it's quite rapidly increased all the way through from pH 7 all the way up past 12, and now it's starting to level off. Now, can anybody actually justify why we've got this kind of rapid change of pH? It didn't happen until we kind of got nearly 1.5 minutes in, which means if we're delivering about 1 centimetre per second, about 30 centimetres cubed, yeah.
I think it might have been because it was taking time to neutralise the acid, and then when it got to a certain point, it started getting better, quicker, because there was enough alkali to neutralise it quicker.
Fantastic.
Then it got to the point where it was the same pH as the alkali in the first place because there wasn't enough acid to neutralise it back.
Absolutely right. You have your acid inside here, your H plus ions, in high concentrations. Then as you're adding your alkali, each one of those H pluses reacts with an OH and takes it out of the equation. So then you still end up with loads of H pluses. And eventually you're going to get to the point where each H plus disappears because it reacts with an OH, producing a water molecule. And then you will end up with a neutral pH. Now we've got no H pluses left anymore. The only thing we're introducing now is an OH minus, which means you're going to have a high concentration of OH minus, no H plus, which means you're going to go alkali, and you're going to get incredibly high pH. Okay. If I was to start this the other way around, say for example, I started with, inside the beaker, before I introduced the stuff from the burette, I started with alkali, and I added acid. What would happen?
The graph would be opposite, wouldn't it? Start at 14 because that's what the alkali on the scale would be, and then it would obviously drop down to neutral, then keep going until it levels out.
That's fantastic. Well done. Absolute reverse. And for very good reasons. The pH would be high, then it would, just like it does here, rapidly drop down, and then you'd end up at a low pH. Yeah? Fantastic. Great. When they actually see the curve changing, it's almost within a few seconds they kind of understood what was going on, and they could see how things were developing because we discussed it beforehand. Now, if you were to do this type of thing without any kind of ICT, you'd be trying to convince them that that's the case, and you'd be very difficult to do so. You'd have to take your solution off, put your universal indicator in, what's the pH now, take it up back in again. It'd be very, very disjointed, and it would be an absolute mess. So the ICT is very quick, very, very fast, and they can see it happening in front of their eyes, and that's what the beauty of the ICT, and it really is a very, very good tool. There's our curve. What I want you to do is to explain what is happening at the different parts of the curve in terms of how many H plus ions I've got and how many OH minus ions I've got. And I'm particularly interested at the pH 7. What can you say about the number of OH minus ions and the number of H plus ions I've got?
But I thought as from here they would start to reduce as they were reaching the neutral, is it?
point, yeah.
And then the OH would start to increase.
That's right. But the thing is, what you're doing is you're introducing your OH minus and your H pluses. And what happens, one of those H pluses reacts with an OH, and they form water, which doesn't have any pH at all.
Yeah.
So what you end up with is every single time you drop an OH in, a H plus goes
Yeah.
and forms water. So the acidity drops a little.
Yeah.
So when you get to this point here, you get to the point when you've virtually got very few H pluses
yeah.
left. What can you say then at this point as the number of OHs and the number of H pluses at pH 7?
They are both the same number.
Brilliant, well done. Absolutely right. Fantastic. So let's try and understand what's going on here then. We've got H plus ions, lots of them.
Yeah.
And what we add into them?
The OH ones?
Good, the OH minus ions. And every one of those H pluses reacts with an OH minus, right?
Yeah.
So as we drop in one OH minus, that reacts with one of the H pluses and they go away. We've still got loads of H pluses down here, haven't we?
Yeah.
Right? So we're going through, and we get to this point here, and now, when we get to here, what can you say about the number of OHs and the number of H pluses at that point there?
Start to become equal.
Start to become equal, good. So then we get to pH 7. When we go past pH 7, why does the pH now go up?
Because there's more OH.
OH minus. And then here, what can you say about the number of OH minuses we've got? Small amount, same
Yeah,
amount,
big.
or loads?
Loads.
Loads, absolutely loads, and that's why it's so alkaline. Okay,
Yeah.
good. And as I go around, a lot of the conversations were, why is it 7 here? Why is it acid here? Why is it alkaline here? And they could pretty much answer those questions for me. And then once they gain that kind of confidence, because it is just confidence, then they start to be more confident in what they're saying and they can understand it much better. So what can you say about the number of H pluses and OHs here?
They're equal
They're equal. Why? How do you know that? What evidence have you got?
because it's neutral.
It's neutral.
7.
pH 7. Good. Right. So therefore, what's happening here then?
They've
Become like
the
more alkaline.
OHs. There's no H plus left.
Brilliant. Absolutely right. Yeah. There's no H pluses left. So all you've got now is an excess of OH minuses, which means it's now alkaline. Okay. All this is about is really kind of, can we predict what's going to happen? Can you justify in terms of the OH plus ions, the OH minus ions, what is actually happening? And the graph gives you the evidence, and it's the kind of instantaneous evidence, and that's the beauty of it.